Hello, everyone. We are Team Verstand, and my name is Yi Gao, and my topic is fast task assignment in large-scale multi-goal task assignment and pathfinding. The problem given in the LRR 2024 competition is a combination of MAPF with rotations and multi-goal TAPF. The TAPF problem is a combination of past task assignment and pathfinding. So TAPF methods can be characterized into coupled and decoupled approaches. Coupled approaches consider task assignment and path planning jointly. Decoupled approaches consider task assignment and path planning independently. Since the coupled approach is too time-consuming and cannot complete the path planning within a single time step, we will primarily focus on the task assignment aspect of the decoupled approach in the following discussion. We divided the instance into three categories based on their scale. Small scale instances include random 1 to random 5. Medium scale instances include city 1 and city 2. Large scale instances include game, sortation, and warehouse. The organizer provides a priority-based graded task method. It assigns a task to agents sequentially based on their IDs, and for each free agent, a free task within the minimum estimated completion distance is selected, calculated as the sum of the agent task distance and the task distance. The greedy algorithm serves as a baseline in our experiments. We conducted our experiments on a Ubuntu server with an Intel Gold 6133 CPU processor and 125 GB RAM. The central algorithm is proposed by Hang in 2017. It uses a Hungarian algorithm. The key point is that it considers not only free agents, but also the agents that have already been assigned tasks but have not reached the first goal of the task. Central algorithm performed optimally on small-scale instances and City 1, but faltered when the number of agents exceeded 3,000 in City 2, exposing limitations in handling high-density environments. However, the grading method has limitations in accurately estimating task completion time. The estimation approximates the minimum task completion distance as task duration, which neglects delays caused by the need to avoid collisions with other agents during task execution. To address this, we developed several adaptive congestion-based methods to estimate the agent task delays, which is defined as the difference between the minimum time an agent required to complete a task and the actual time an agent consumed to complete a task, while the minimum time an agent required to complete a task is the sum of agent task distance and task distance. Our algorithm's features are highlighted with blue shading. They all estimate the agent task delays based on the congestion level around the first goal location of the task. And the adaptive congestion coefficient gamma is calculated based on all the finished tasks in the past. And these algorithm differences lies in the regions and the counting objects chosen for congestion evaluation. The first congestion evaluation method we introduced is count agent in the task agent circle. CATAC evaluates congestion around each free task by defining an task agent circle centered at the task first goal location with a radius equal to the agent task distance, and the number of other agents within this circle is counted. The right figure shows congestion computation when agent A1 selects task tool 2. G12 in the square stands for the first goal location of task 2. As we can see, there are 3 other agents in the circle range, so the congestion value is 3. CATAC consistently outperformed grading in small and medium scale settings, but lagged behind Central and NMS. Another congestion evaluation method we introduced is count intersection between agent task vector and agent goal. CIATAG calculates the number of intersection points between a specific free agent task vector and the agent goal vector of occupied agent. The agent task vector represents the vector from the current location of the free agent to the first goal location of the task, while the agent goal location represents the vector from the current location of the occupied agent to the next goal location. The key insight here is that a higher number of intersection points between an agent task vector and multiple agent goal vectors can lead to increased delays for the free agent as it navigates towards the first goal location of the task. CIATAG achieved top result on the game instance. Count agent in the task square. Cats divides the map into fixed k times k square regions. Cats determines the square in which the first goal of each free task belongs and counts the number of agents within that square before iterating over each free agent. In the right figure, there are 3 other agents in the first goal square, so the congestion value is 3. Because these square boundaries are static, so the computed agent counts for square apply to all free agents estimating congestion in that range, which means this value can be reused. This significantly reduces the computational overheads by avoiding repetitive calculations, thus improving efficiency, especially in scenarios with a larger number of agents and tasks. Cats ranked highest on sortation and second on warehouse, which underscores its effectiveness on large-scale instance. Task square density times agent task density. Both in this method, both the number of agents and the static obstacles are taken into account. Agent density rho is calculated as a ratio of the number of agents in the square to the number of blank cells within that square. Rho is multiplied by the distance between the current location of the agent and the first goal location of the task. TSDA-TD excelled on warehouse and performed competitively on sortation instance, which underscores its effectiveness on large-scale instance. We ranked second in the task scheduler rank. And in the future, we may consider agent priority before task assignment, but during the procedure of task assignment. And this wraps up my talk. Any questions?
Yes, thanks, Ye, for the wonderful talks. So adding questions from participants. So you can either raise your hand or just feel free to unmute yourself.
So hey, yeah. Thanks for your wonderful talk. So I think I have one question regarding your approach. So your delay estimation. So am I understanding it correctly? It is actually some sort of penalty, congestion penalties that you put onto the assignment so that you penalize the task assigner to avoid severe congestions in the environment.
Yes. It estimates the delays by counting some object around the first goal locations. So yes, it is a penalty added to as shown in the line 14. We add this estimated delay to the task distance.
Okay. Oh, thank you. So have you think about like so I think it looks like the current approach is more of like handcrafted. Have you think about like to make it some sort of machine learned penalties? Do you think that will uh, like surpass your handcrafted implementations?
Thank you for your suggestions. Maybe I can try this in the future. Yeah.
Okay, thank you.
So I also have a very short question. It's just regarding different approaches you share on the results table. Is that individual approaches results or is that one add up another?
Which method?
I mean, in the experiment result, is that like the different approaches, like is that especially the last several ones, is that one at another, or is that just like different approaches and behavior like based on single maps?
All my congestion-based approaches share the same framework. Their difference lies in how they evaluate evaluate congestion around each free tasks. Yes, which means their difference lies in the 13 line of the of algorithm 2. And in this algorithm, we add two. Oh, yeah. And in this algorithm, we add two lines before task assignment, which is count the number of agents in each square and compute each free task first goal in which square. This means that this data can be reused, thus reduce the computation times.
Okay, thank you. So also thanks again for contributing this wonderful talk.